So let's dive in a little bit deeper with some of these concepts. Encoding refers to the process of transforming data from one format into another. And typically, this is using a set of predefined rules. Now, unlike cryptography, which focuses on security, encoding primarily serves the purpose of representing data in a more suitable form for specific applications or systems. So while encoding does change the representation of data, it doesn't necessarily ensure confidentiality or protection against unauthorized access. One example would be base64 encoding, which is a specific type of encoding that converts binary data into text-based format. It's commonly used to ensure that binary data can be safely transmitted in text-based mediums, such as email attachments. This encoding scheme works by representing each set of 3 bytes in the binary data as a group of 4 characters in the ASCII character set. And while base64 encoding doesn't provide security on its own, it's widely utilized for its ability to convey binary data through text-based channels. We can see also another form of encoding of URL encoding, also known as percent encoding, and this involves replacing special characters in URLs with specific codes to ensure compatibility with web browsers and web servers. Since URLs have specific reserved characters that serve particular functions, encoding these characters prevents confusion and misinterpretation. For instance, spaces are often replaced with %20, and other characters are similarly represented to prevent ambiguity in URLs. And while URL encoding doesn't focus on security, it does ensure that URLs can be correctly processed by web applications and browsers. Let's now review hashing a little bit more in depth. And recall that hashing is a fundamental cryptographic technique that involves transforming input data into a fixed length hash value, also known as a digest. And this process is designed to produce a unique output for each distinct input, even if the input is only slightly different. This uniqueness of hash values makes it possible to identify data based on just the hash value. Hashing, as a result, plays a crucial role in various security applications, including data integrity verification, password storage, and digital signatures when you don't need to know exactly what the original input data was or its decrypted state, but just need to do a trust or integrity verification check. Now, one key property of hashing is that the same input will always produce the same hash value. This deterministic nature ensures predictability, and it makes it suitable for tasks where data integrity needs to be verified over time, every time. For instance, organizations can hash files and compute their hash values periodically to detect any alterations. Finally, hashing algorithms are diverse, and each algorithm generates a unique hash value for a given input. Some of the common hash functions include MD5, SHA-1, and SHA-256. While MD5 and SHA-1 were widely used in the past, they are now considered weak due to vulnerabilities such as collision attacks. And collision attacks are where different inputs produce the same hash value. Consequently, stronger hash functions like SHA-256 are preferred for their resistance to such attacks, ensuring a much higher level of security in applications that rely on hashing. Now let's do a bit of a dive into symmetric encryption. And this is a cryptographic technique that employs a single secret key for both the encryption and decryption processes. This approach is known for its efficiency and speed, making it particularly suitable for scenarios where large volumes of data need to be securely transmitted or stored. Now let's walk through the process of how this actually works. First of all, in symmetric encryption, the key exchange between the sender and receiver is a critical step. Both parties generate a shared secret key, which remains confidential between them. The encryption process involves converting plain text into ciphertext using the shared key and a specific encryption algorithm. The resulting ciphertext is then sent over an insecure channel. At the receiver's end, the same shared key and decryption algorithm are used to reverse the encryption process and obtain the original plain text. Now, there are some advantages to this. Symmetric encryption offers several. Its speed and efficiency make it well suited for handling substantial amounts of data quickly, Moreover, due to its less computational intensive nature compared to asymmetric encryption, symmetric encryption requires fewer resources for processing. And despite all of its benefits, symmetric encryption does pose some challenges. Securely exchanging the shared secret key between parties without interception is essential, and that's not easy. Additionally, when multiple users are involved, each pair of users needs a unique key for secure communication, potentially leading to complexities in key management with more moving parts. And an example of symmetric encryption is something that web browsers use every single day. When we exchange our keys between an encrypted session, we actually are using AES as the symmetric encryption algorithm to securely encrypt our data after the initial asymmetric key exchange has taken place. Now let's look at asymmetric encryption by comparison. And this one is different as it uses a public key for encryption and a private key for decryption. And the process involves several steps. The recipient generates a key pair with the public key distributed openly and the private key kept secret. When sending a message, the sender will use the recipient's public key to encrypt it, and that results in ciphertext. This encrypted message can then be safely transmitted over any insecure channel. The recipient only has to go and grab their private key to decrypt the ciphertext and retrieve the original plaintext information. Now, there are some serious advantages to this, and truthfully, they both work in tandem as a result. Asymmetric encryption eliminates the necessity for a secure key exchange, which is required for symmetric encryption, and this is due to the fact that the public key is openly shared. Additionally, asymmetric encryption allows the creation of digital signatures, which offers robust authentication and non-repudiation. However, challenges do exist. The computational demands of asymmetric encryption are higher due to intricate mathematical operations. This can lead to a slower performance compared to symmetric encryption. Moreover, longer key lengths are required to achieve the same level of security, which again can increase computational overhead. One of the most common and prominent asymmetric encryption algorithms is RSA, for Reverse Shamir Edelman. This is commonly used when a browser wants to connect to a website securely. It'll use RSA to exchange the shared secret symmetric key so that they can both communicate in a secure manner. Now let's take a look at digital signatures and see how all of this can be combined together. Digital signatures play really a pivotal role in ensuring the authenticity and integrity of digital messages or documents. They provide a mechanism for verifying the source of the content and detecting any tampering or alterations. So let's look at this signing and verification process. And the process begins with the sender generating a digital signature using their private key. And this signature is unique to the specific message or document. Upon receiving the message, the recipient uses the sender's public key to verify the digital signature's authenticity and integrity. And zooming in a little bit into the verification steps itself, we have the message digest portion. So to begin the verification process, the recipient creates a fixed size message digest or hash of the received message. This hash serves as a compact representation of the original content. Then we have the decryption component, where the recipient then employs the sender's public key to decrypt the digital signature. This decryption step results in the extraction of the original message digest that was created during signing by the sender. Finally, there's a comparison step. The recipient will compare a calculated hash obtained from the decryption process with the original hash computed from the received message. If the two hashes match, it indicates that the digital signature is valid and the content has not been tampered with. Finally, let's talk about the future of cryptography. The emergence of quantum computers introduces a significant paradigm shift in computing power. Quantum computers can effectively solve problems that would take classical computers like ours truly an inordinate amount of time, and this potentially undermines the security of current cryptographic systems like RSA. And then there's post-quantum cryptography, and this is where, recognizing the impending challenges posed by quantum computing, researchers can actively be engaged right now in developing post-quantum cryptographic algorithms. These algorithms aim to provide resistance against attacks from quantum computers. Next, we have blockchain technology, and I'm sure you've heard about this. Blockchain leverages cryptographic techniques to maintain the integrity and security of data in decentralized manners. Through cryptographic hashing, digital signatures, and consensus mechanisms, blockchain establishes an immutable record of transactions that is highly resistant to tampering. And this technology right now is at the forefront of transforming industries such as finance, supply chain, and more by enabling secure and transparent data exchange without the need for intermediaries. And then finally, there's the concepts right now of homomorphic encryption. And this is more on the cutting edge right now as a field of research aimed at allowing computation on encrypted data without the need for decryption. And this is pretty revolutionary when you think about it. This preserves the confidentiality of sensitive information, yet still enabling valuable computations to be performed. So this holds immense potential for enhancing data privacy in scenarios like cloud computing, where data is processed on external servers while remaining encrypted, and honestly mitigating privacy concerns as a result. Truly, it's an exciting time to be discussing the future of cryptography.